You're floating in a metal capsule the size of a small apartment. Through the window, Earth is already gone, reduced to a faint blue speck barely visible against the black. You turn to look ahead. Nothing. Just void stretching infinitely in every direction. This is deep space, and humans cannot survive here. Might not, or probably won't. Cannot. The reasons why have nothing to do with technology or preparation. They're written into the fundamental laws of physics and biology. On paper, it all makes sense. We've walked on the moon, we've built orbital stations, we've sent robots to the outer planets. Deep space should just be the next step. Better ships, more fuel, smarter technology. Except the math breaks. There's a threshold, a point in space where everything that keeps you alive starts to unravel. Past that line, survival stops being about innovation or willpower. It becomes a fight against physics itself, and physics doesn't compromise. Your resources deplete, your shielding fails, your body begins to disintegrate. The further you go, the less reversible any of it becomes. This isn't speculation, this is what will happen. Deep space doesn't just challenge human survival, it systematically dismantles every mechanism that makes it possible. And once that process begins, there's no stopping it. Let's begin with the fundamentals. Humans require three things to stay alive: oxygen, water, and food. On Earth, we're surrounded by abundance. Rivers flow endlessly, the atmosphere recycles itself, plants convert sunlight into energy. It's a closed-loop system perfected over billions of years. In space, that system doesn't exist. Every breath you take has to be manufactured. Every drop of water must be recycled from your own waste. Every calorie consumed has to be carried from Earth or grown in conditions so artificial they barely work. The International Space Station, humanity's most sophisticated orbital platform, recycles approximately 90% of its water. That sounds efficient until you calculate what it means over time. 10% loss doesn't sound catastrophic, but it accumulates relentlessly. On a mission to Mars, just 7 months each way, that 10% compounds into thousands of liters you must carry as backup. For journeys measured in years, the numbers become impossible. But here's where it gets worse. Those recycling systems aren't passive. They're extraordinarily complex machines. Pumps, membranes, chemical processors, sensors. Every component requires maintenance. Every part eventually fails, and all of it demands energy. Massive amounts of energy. The ISS generates power through enormous solar panels bathed in constant sunlight, but solar energy diminishes with distance. At Jupiter's orbit, you receive only 4% of the energy available near Earth. At Neptune, it drops to 0.1%. Beyond that, in true interstellar space, the sun becomes just another star, functionally useless. Nuclear reactors could compensate, but reactors need fuel, and fuel depletes. When it runs out, every system shuts down simultaneously. Air production stops, water recycling halts, temperature regulation dies. The spacecraft transforms from a habitat into a coffin, tumbling silently through the infinite dark. You might think the solution is obvious: bring more supplies. That creates the next problem. So even if we build perfect recycling systems, recovering 99% of resources, time still wins. Missions to deep space aren't measured in weeks. They're measured in years, decades, potentially generations. Over those timescales, even fractional losses become absolute deficits. Every single day, the margin for survival shrinks until one day it reaches zero. And here's what makes resource depletion particularly insidious. You can't know exactly when you'll hit that 0 point. Small inefficiencies compound unpredictably. A slightly degraded filter here, a minor seal leak there, a recycling membrane operating at 97% instead of 98%. These microscopic failures accumulate in ways that are impossible to model with precision. By the time you realize you're running out, it's already too late to course correct. The mathematics of survival becomes a countdown you can't stop. Every kilogram launched into space costs enormous resources and requires fuel to accelerate. The more mass you add, the more fuel you need. But fuel has mass too, which means you need additional fuel just to move the fuel. It's an exponential trap with no exit. This is the tyranny of the rocket equation, a mathematical reality that doesn't care about ambition or innovation. A human needs roughly 2 kilograms of water per day, 0.8 kilograms of oxygen, and 0.6 kilograms of food. For a crew of 6 on a 10-year mission, that's over 74,000 kilograms just for basic consumables, assuming perfect recycling, which doesn't exist. Add recycling equipment, radiation shielding, propulsion systems, habitat modules, and you're pushing millions of kilograms. Every kilogram cascades into more fuel requirements, which adds more mass, which requires more fuel. The equation spirals until the mission becomes physically impossible to launch. So you're trapped. You can't carry enough, you can't recycle perfectly, and you can't resupply. And here's the cruel irony. The lighter you make the spacecraft, the more vulnerable it becomes. Thinner walls means less radiation protection, smaller reserves mean less margin for error. You're forced to choose between impossible options, too heavy to launch or too fragile to survive. This creates what engineers call a design paradox. Every solution to one problem makes another problem worse. Need more shielding? Add mass. Need less mass? Reduce shielding. Want longer missions? Carry more supplies. Carrying more? Can't accelerate fast enough. The optimization space simply doesn't contain a viable solution. You're not solving a difficult equation, you're trying to satisfy mutually exclusive constraints. Proxima Centauri, the nearest star system to Earth, sits 4.24 light-years away. Our fastest spacecraft ever built, the Parker Solar Probe, traveling at 692,000 kilometers per hour, would require over 6,000 years to reach it. 6,000 years, longer than recorded human civilization. Even within our solar system, distances are crushing. Mars is 6 to 9 months away, Jupiter requires years, Neptune over a decade, one way. But distance alone isn't the killer, what fills that distance is. Every meter of space is a shooting gallery of objects moving at velocities that turn physics into a weapon. The further you travel, the more exposure you accumulate. The probability doesn't decrease with time, it multiplies. And distance creates another problem people rarely consider: communication lag. On Mars, there's a 20-minute delay each way. You can't call for help in real time. You can't troubleshoot urgent problems with experts on Earth. By the time ground control receives your distress signal and sends a response, the crisis has already resolved itself. One way or another, beyond the outer planets, that lag extends to hours. In interstellar space, years. You're not just physically isolated, you're temporarily isolated. Every decision must be made alone, in the moment, with no second opinions. Space isn't empty. Billions of objects drift through the void. Asteroids, comets, dust particles, micrometeorites, all traveling at velocities that turn microscopic fragments into bullets. A grain of sand impacts spacecraft at speeds exceeding 50,000 kilometers per hour. At that velocity, it punches through metal, it shatters viewports, it destroys electronics, it kills instantly. The ISS carries specialized shielding and regularly performs evasive maneuvers to avoid tracked debris. In deep space, there's no tracking network, no warning, no evasion. A single impact to a critical system and the mission ends. Hull breach, atmosphere gone in seconds, power supply hits, you freeze in darkness. The water system is destroyed, you die of thirst. The mathematics are simple. The longer you're exposed, the higher the probability of impact. A 1-year mission has X probability of catastrophic collision. 10 years multiplies that, 20 years multiplied again. The curve climbs steadily until the question stops being if and becomes when. And shielding doesn't solve this, it delays it. Every impact degrades whole structure. Microscopic fractures accumulate, material fatigue compounds. A spacecraft rated for 20 years might fail at 15, then 10, as damage reaches critical thresholds. The ship is dying by inches. What makes this truly inescapable is the vastness of the threat volume. Near Earth, we track objects larger than 10 centimeters and can predict collisions. In deep space, you're traveling through billions of cubic kilometers of unmonitored space filled with debris we've never catalogued and never will. The universe isn't trying to kill you. It doesn't need to be tried. The sheer statistical probability of your trajectory intersecting with something lethal approaches certainty over sufficient time. On Earth, when a machine breaks, you call a technician, you order parts, you fix it. In deep space, mechanical failure means death. Air conditioning malfunctions, temperatures swing to extremes, a sensor fails, a pump seizes, a seal cracks. External repairs require spacewalks, inherently life-threatening. One torn suit and you're dead. Internal repairs face different limits, cramped space, finite spare parts, no expertise beyond the crew. If a critical component breaks and you lack a replacement, the mission is over. But failures don't stay isolated. One system collapses, overloading a second, which damages a third, cascading failures with nothing to stop them. Here's what makes it inevitable. Mechanical systems fail predictably. Early in the mission, manufacturing defects appear. Then there's stability, but eventually every component enters the wear-out phase simultaneously. They are all installed at the same time. 10 years in, everything fails at once. Air scrubbers, water processors, electrical systems, all hitting end of life together. You can't replace everything. You watch your survival margin evaporate system by system. We maintain a space station 400 kilometers above Earth, barely outside the atmosphere, and survival there requires constant ground support. Every day is a managed emergency. But even if we solved every engineering problem, one barrier remains absolute. Our biology. Because spacecraft can theoretically be designed for redundancy, for repair, for extended operation, but human bodies can't be redesigned. They come with fixed specifications determined by evolution, and those specifications have an operating envelope that deep space violates in every possible dimension simultaneously. On Earth, two shields protect us from cosmic radiation, the planet's magnetic field and atmosphere. Together, they deflect or absorb high-energy particles constantly bombarding our solar system. In deep space, both shields vanish. Every second, galactic cosmic rays and solar particles tear through your body, shredding DNA, destroying cells, triggering mutations. These aren't controlled medical X-rays. These are particles with energy so high that conventional shielding becomes worthless. On Earth, background radiation averages 3 millisieverts annually. ISS astronauts receive approximately 150 millisieverts per year, 50 times higher. In deep space, exposure skyrockets further. NASA's career limit for astronauts is 1 sievert, a 3% increase in fatal cancer risk. A round-trip Mars mission approaches or exceeds that. A multi-year deep space voyage blasts past it. After just a few years beyond Earth's protection, cancer becomes a certainty, and this damage is cumulative and irreversible. Unlike a sunburn that heals, radiation damage to DNA builds up permanently. Cellular repair can't match incoming damage. Even if you return to Earth, the damage persists, a genetic time bomb. Worse, as your DNA degrades, your cells lose their ability to repair other damage. Bone loss accelerates, muscle atrophy worsens, immune function collapses faster. Each form of damage amplifies the other until your biology is caught in a death spiral. The insidious part about radiation is its invincibility. You can't see it, you can't feel it hitting you, there's no pain, no immediate symptom, no warning that you've just absorbed a dose that will kill you 20 years later. You're being destroyed at the molecular level every single second, and your body has no way to signal the danger until it's far too late to matter. Floating effortlessly through space seems peaceful. It's catastrophic. Without gravity, muscles atrophy and bones lose density at 1 to 2% per month. After 1 year, you've lost 12 to 24% of bone mass. After 5 years, your skeleton is structurally compromised. ISS astronauts train 2 hours daily using specialized resistance equipment. They still lose bone mass, particularly in hips, spine, and legs. In zero gravity, the body recycles what it deems unnecessary. After years in space, Your bones would be as fragile as an 80-year-old with severe osteoporosis. Imagine arriving at a distant planet after a decade-long journey. You step onto solid ground. Your legs shatter under normal planetary gravity because your skeleton can no longer support your body weight. All those years traveled, and you can't stand. Your heart weakens because it no longer pumps against gravity. On Earth, your cardiovascular system works constantly to push blood upward. In space, that resistance vanishes. The heart shrinks. Blood redistributes abnormally, pooling in your head. Chronic facial swelling, increased cranial pressure swells your optic nerve and deforms your eyeballs. Some astronauts return with permanent vision damage. Your immune system collapses. Infection resistance drops. Catastrophic when simple infections become lethal with no hospital. Wounds heal slower. Dormant viruses reactive. Herpes, chickenpox resurface. Your sense of balance fails. The inner ear organ becomes useless, causing constant disorientation, spatial confusion, and severe motion sickness. Bone loss releases calcium into your bloodstream, kidney stones. Muscle atrophy includes your diaphragm. Breathing becomes more difficult. Vision problems impair repairs, increasing errors. Every failure makes the others worse, and there's no adaptation. Your body doesn't learn to function in zero gravity. It deteriorates. Evolution shaped us for Earth's gravity over hundreds of millions of years. You can't reverse that with exercise and hope. The longer you stay in weightlessness, the more you become something that can't survive anywhere, not in space, and eventually, not even back on Earth. Years confined in a metal container, surrounded by infinite emptiness, no escape. You can't go outside, you can't feel wind or rain. Every day is identical, same walls, same faces, same artificial lighting your body never adjusts to. Sleep disorders become universal, no natural day-night cycle. Depression, anxiety, cognitive decline, all documented on 6-month ISS missions. On journeys spanning years or decades, the human mind fractures. Isolation studies show that even carefully selected, trained individuals break down psychologically after extended confinement. Those studies have emergency exits. In deep space, there is no door, no rescue, no way out. You're trapped until the mission ends or until you die. As your body deteriorates, your mental health worsens. As mental health declines, you become less capable of maintaining routines that slow physical deterioration. Depression reduces appetite. Anxiety disrupts sleep, impairing cognition, increasing critical errors. Another spiral with no bottom. Our bodies are the product of millions of years of evolution on Earth. Every cell, every system is precisely calibrated to specific conditions. Gravity, atmospheric pressure, filtered radiation, circadian rhythm. We are Earthlings. In space, this biological machine systematically fails. It's like removing a fish from water. Technically different environments. Biologically, the difference between life and inevitable death. And perhaps most disturbing, the psychological damage may be the first thing to break catastrophically. Before the radiation kills you, before your bones crumble, before the systems fail, your mind might give out, and when it does, you become a threat not just to yourself but to everyone aboard. One person's psychological collapse in a confined space can trigger failures in others, creating a cascade of mental disorientation that dooms the entire crew. The mission fails not because the ship broke, but because the people inside it did. So here's the reality. Deep space survival isn't just challenging, it's a war of attrition against physics, biology, and time, a war we cannot win. The problem was never distance, it was what distance does to everything else. The further you travel, the more systems fail, the more radiation accumulates, the more your body deteriorates, and unlike missions near Earth where you can abort and return home, deep space missions cross a point of no return. Beyond that threshold, turning back stops being an option. The fuel is spent, the damage is done, you're committed. That's the barrier, not insufficient rockets or inadequate engineering. Human biology has hard limits, and deep space systematically exceeds every single one. We are the product of 4 billion years of evolution, precisely calibrated for one planet, one gravity, one atmosphere, one magnetic field. That calibration isn't a design choice, it's what we are. and deep space doesn't accommodate what we are. We can build larger ships, we can dream of distant stars, we can plan missions spanning generations, but the moment those missions leave Earth's protection, they stop being voyages of exploration, they become experiments in controlled deterioration. And once that deterioration begins, it doesn't stop, it compounds, day by day, year by year, until the mission designed to carry humanity to the stars becomes a sealed container drifting silently through the void with nothing living inside. That's not pessimism, that's physics, and physics is non-negotiable.